Imagine taking the energy output of thousands of galaxies, pulling it from billions of individual stars, and compressing it down into a single, focused weapon. During the Cold War, the United States launched the Vela spy satellites to detect illegal nuclear detonations in the atmosphere. Instead of atomic bombs, those satellites picked up mysterious, incredibly powerful flashes of energy coming from deep space. Unlike the visible light that harmlessly illuminates our days, gamma rays are a form of high-energy ionizing radiation. A single gamma-ray photon carries more energy than 1,000,000 visible light photons combined, giving it the raw power to literally rip atomic bonds apart. If a burst like this hit Earth, the gamma radiation would rapidly deplete our protective ozone layer. Without it, lethal levels of ultraviolet radiation from the sun would pour into the atmosphere, effectively cooking the surface of our planet. Because gamma rays are a form of light, the beam travels at exactly the speed of light. No early warning system could ever alert us. By the time our telescopes saw the flash, the radiation would already be here. We are navigating a cosmos inhabited by invisible, silent snipers that fire blindly into the dark, capable of eradicating a biosphere before anyone even realizes the trigger was pulled. This animated diagram compares a standard supernova with a gamma-ray burst. When a typical massive star explodes, it releases its energy outward as a steadily expanding sphere. A gamma-ray burst, however, concentrates its energy into two intensely focused, opposing polar beams. For the longest-lasting gamma-ray bursts, the engine driving this beam is called a collapsar. This occurs when a massive, rapidly rotating star completely exhausts its nuclear fuel, and its core collapses directly into a black hole. Because the star is spinning so quickly, the outer layers of the star can't simply fall straight down into the center. Instead, that infalling material flattens out, forming a violently churning, hyperaccreting disk around the newborn black hole. Inside that swirling disk, twisting magnetic fields and the annihilation of subatomic particles generate immense pressure. The only way for that pressure to escape is straight up and down, violently launching a jet of energy through the star's poles at 99.99% the speed of light. A gamma-ray burst is essentially a failed supernova. The star's chaotic explosive force gets trapped by its own gravity, refined by its rapid rotation, and violently redirected out into the cosmos as the universe's most powerful, focused blowtorch. There is a second engine capable of producing these bursts. Instead of a single collapsing star, two extremely dense stellar remnants, known as neutron stars, spiral rapidly toward each other until they violently collide. This collision triggers a short gamma-ray burst. The event itself lasts only about a single second, but it generates a tightly focused beam of energy that rivals the explosive output of an enormous collapsar. The extreme heat and pressure of two neutron stars smashing together also acts as a cosmic forge. The collision manufactures these heavy elements through rapid nuclear reactions, creating the universe's gold, its abundant silver, and dense platinum. The exact same astrophysical mechanism responsible for firing a planet-sterilizing death beam is also the sole manufacturer of the most precious materials in human history. Earth may have already been caught in the crosshairs. About 450 million years ago, the Ordovician mass extinction wiped out 85% of all shallow water marine species. Astronomers theorize the destruction observed in the fossil record matches a gamma-ray burst strike perfectly. We have physical evidence of a much closer, milder encounter. Tree rings from the year 774 AD show a massive, anomalous spike in radioactive carbon-14. Researchers calculate a distant gamma-ray burst grazed our planet 1,200 years ago, washing over the atmosphere without causing mass casualties. These strikes present a chilling solution to the Fermi Paradox. Gamma-ray bursts might function as a cosmic filter, regularly sterilizing hospitable planets and keeping the universe relatively devoid of advanced, intelligent life. This map illustrates what a strike requires. First, the source must be within 8,000 light-years. Second, the 5-degree cone must perfectly align with Earth. Furthermore, Milky Way stars shed too much mass to form collapsars. We observe them mostly in distant, metal-poor dwarf galaxies. When you run the astronomical math on proximity, alignment, and stellar composition, the odds of Earth getting hit by a lethal gamma-ray burst by the year 2050, or even in the next million years, are functionally zero. Gamma-ray bursts are undeniably the most terrifying forces in the cosmos, but the hyperspecific, exceedingly rare astronomical conditions required to forge them mean our quiet corner of the solar system remains a remarkably safe haven.